And we're going to skip the first section of chapter 10, which is all about conic sections. So we're assuming that we all know a little bit of something about conic sections, hyperbolas and ellipses and circles and parabolas and that kind of thing. So we're jumping right into section 10.2. So we're going to talk about parametric equations today. So far in what we've done this semester, we've been talking about functions or equations where one variable is a function of another. Parametric equations is we have a situation where each variable is a function of a third variable, and that third variable is called our parameter. And our parameter can be lots of different things. We'll use lots of different parameterizations of equations depending on the situation. One classic example that we probably are familiar with is projectile motion, where we have x for projectile motion v0t plus x0. So our position in v0 and x0 are our initial velocity and initial position. So x is a function of t, and then y in projectile motion, we have 1/2 at squared plus v0t plus y0. So this is our this would be an example of parametric equations that we may have seen before with projectile motion. So each variable is a function of the parameter t. Usually it's time for projectile motion, but we'll parameterize in a lot of different ways. The path of a set of parametric equations is called, we call it a plane curve. So I'm just talking about a little terminology here. So when you see these terms in your textbook when they're talking about a problem or something, so the path of a set of parametric equations is called a plane curve, and then if we have this set of parametric equations, the set of points that are described by those equations is called the graph. So if we the set of points, we call the set of points the graph. So the path is a plane curve. The set of points described by the parametric equations. And then the graph along with the set of points is what is how we describe the plane curve. So the path is the set of points plus the equations. And we call the plane curve C. So if we take our equation, we put it together with the set of points that it describes, we get what we call a plane curve. Usually we just talk about the graph, or we talk about the curve, or we talk about the graph of the parametric equations. I just want you to have seen this terminology so that when it comes up in a problem, if they say the plane curve, they use these terms, you have some idea of what they're talking about. We're not going to make a big distinction over these things, but I just want you to have seen the terms. So one thing that we're going to be doing with parametric equation, to help us sketch a graph, is we may want to eliminate the parameter. It might not be clear if we have a set of parametric equations what the graph is going to look like. So in order to see what the graph is going to look like, we eliminate the parameter. So that's the first thing that we're going to talk about, is eliminating the parameter. And the main purpose of eliminating the parameter is to help us sketch a graph of these functions. And we will get to the point where certain kinds of parametric equations we will be fairly familiar with. And when we see them, we'll know, oh, that the graph of that is a such and such. So to eliminate the parameter, we want to start with the equations. We want to solve for the parameter in one equation. And then we substitute into the other. And then if we're given some kind of domain for our parameter, we need to adjust our domain so that the domain of our new function matches the domain of the given by the parameter. So let's look at an example here. We want to, in this particular example, we want to eliminate the parameter. And we want to sketch the graph. And here are my equations. My set of parametric equations. X equals 1 over square root of t plus 1. And y equals t over t plus 1. And we want t greater than negative 1. So looking at this set of parametric equations, I wouldn't know, just looking at this, what kind of curve this describes. We want to sketch a graph, so we're going to eliminate this parameter. So looking at these, anybody have an idea how could we proceed? How would we eliminate a parameter? Looking at x and y, which one looks like it's going to be easiest to work with? We have x, several x's. So those of you that said x, why would x be easier to work with? There's only one t. Here we have a t in the numerator and the denominator. So that, to me, that says that's going to be more complicated. So let's work with the x. So I want to solve for t here. So I get x squared equals 1 over t plus 1. And then
Can we substitute that into the y equation as before and find the other two?
so I could go from here and say that y is t times 1 over, or sorry, x is, y is t times 1 over, or t times x?
Yeah. Well, t times x squared.
T times x squared, yes. So I could do that directly from here. So what Max is saying is this y equals,
I mean, I wouldn't finish it, but
right, but that would save us some work.
Yeah.
Y equals t times 1 over t plus 1. And 1 over t plus 1 is x squared. So I can substitute that in. I was going to do a little more work, but Max saved me some work here. I was going to solve this for t and then substitute it in. This will save us a little work. So y equals t times x squared. And from this one we get t equals y over x squared. Now I can substitute that in here. For t, usually we want y equals to sketch our function. So I'm going to substitute that in here, and I get y equals y over x squared over y over x squared plus 1. Does this help us out? We can simplify this. Should we keep going, or should we use another tactic? Let's just keep going. Let's see where this takes us. So we get. I'm going to find the common denominator here in this denominator. So I get y equals y over x squared over y plus x squared over x squared. So I just found a common denominator down here. Now I'm going to flip this denominator over, multiply by the reciprocal here. So I get y equals y over x squared times x squared over y plus x squared. My x squares cancel, and I get y equals y over y plus x squared. This is getting complicated, isn't it?
Come on, Max.
No, it was worth a try. It was worth a try. So that sometimes that happens when you're eliminating the parameter. There's nothing wrong with trying something out and not getting anywhere. So so let's so what do we want to do? You want to keep going?
Divide both sides by y and then multiply the denominator over.
So Dylan says let's divide both sides of the equation by y.
Yeah.
Right, just get x in terms of t. Shall we go back and do that? Okay. Okay, so let's do Dylan's suggestion, then we'll go back. So Dylan says let's divide both sides by y. So I get
1 equals 1 over y plus x squared.
so we divide both sides by y. Then I clear this fraction. Finally I get y plus x squared equals 1. So finally y equals 1 minus x squared. And we're done. So that wasn't too bad. It wasn't too bad. So let's go back to the other technique and solve this equation for t and then substitute. So we have one expression. We have one path. That wasn't too bad. That wasn't too bad, Max. I apologize. So this is one way we can get there. Let's change the page and we'll start back from here. Okay? So we have what did we have? X squared equals 1 over t plus 1. And we have y equals t over t plus 1. So we're going to solve this. We're going to solve this for t. So I get t plus 1 equals 1 over x squared. Multiply both sides by t plus 1, divide by x squared. So t equals 1 minus, or 1 over x squared minus 1. And I'm going to substitute that into here. When I substitute, we're going to get something that looks kind of familiar. So we're going to substitute in here for t. Y equals 1 over x squared minus 1 over 1 over x squared minus 1 plus 1, right? Let's see, t is 1 over x squared minus 1. 1 over x squared t plus 1. Hang on, let me make sure this is t 1 over. This is t, right? Minus 1 plus 1. Okay. So we get from here, we get y equals 1 over x squared minus 1 over 1 over x squared. Is that right? Is that what we end up with here? Yeah? Everybody agree? Okay. And then I need the common denominator here, so I get y equals 1 minus x squared over x squared over 1 over x squared. When I divide by 1 over x squared, my x squareds cancel, and I get y equals 1 minus x squared. So we get to the same place. So y equals 1 minus x squared. Finally, that's what we got that two different ways. So we eliminated the parameter, substituted, solved for the parameter, substituted into the other equation, we get y equals 1 minus x squared. Now we want to graph this. What does the graph of this equation look like? So we're going to sketch a quick graph. What is it? Parabola. And where's the vertex? Well, first off, does it open up or down? Opens down. And the vertex is at y equals 1. And we set our domain. Let's go back here. Our domain is t is greater than negative 1. So if t is greater than negative 1, that means x has to be greater than if t is greater than negative 1, when t is negative 1, so we're greater than negative 1. So t is greater than negative 1. So x is greater than t, let's think about it. T is greater than negative 1. T is negative 0.9999999. X equals 0, essentially. So x has to be greater than 0. If t is greater than 1, x is greater than 0. So that's we said we had to adjust our domain. So we get an open dot here. Our parabola opens down. And it intersects the x-axis at what point? When y equals 0, x equals 1. There we go. And then the other thing we're interested in with parametric equations is what we call the orientation. Which direction do we travel along the curve as the parameter increases? So let's look back at our original parametric equations. As t increases, does x increase or decrease? As t gets larger, x decreases. Yes? We all agree? So as t gets larger, as we travel along, t equals negative 0.999, et cetera, we're going to travel along the curve from right to left. So our orientation is right to left. So we're going to be interested in the orientation of our curves as we move forward. So this is our equation. This is our graph. We've eliminated the parameter. We adjusted the domain. And as t increases, x increases. So we're traveling along this curve from right to left. So our orientation is right to left. A little bit long, but not too bad. Just a little bit of algebra involved here. So this is how we sketch a graph of a parametric equation. Let's look at it a little bit. Let's go backwards and look at a little bit easier example of this. So questions on the idea here of eliminating the parameter and sketching the graph. Okay. Let's do an easier example. So same thing. We want to eliminate the parameter. Eliminate the parameter and sketch the graph. X equals t minus 1. And y equals 2t squared minus 4t plus 1. So this one's a little easier. My domain is 0 less than or equal to t less than or equal to 2. So this one's going to be a lot easier to eliminate the parameters. T equals x plus 1. I substitute. So y equals 2 times x plus 1 squared minus 4 x plus 1 plus 1. Simplify this, I get y equals 2x squared minus 1. In my domain, 0 less than or equal to t less than or equal to 2. So what are going to be the values of x that I get out of this? Negative 1 less than or equal to x less than or equal to 1. 0, t between 0 and 2, so x is between negative 1 and 1. All right, so we can sketch a graph of this. What is the graph of this function? Parabola opens up, vertex, negative 1. All right. I'm going to go like so. When x equals negative 1, y equals negative 1. So that's where my graph's going to stop. And when x equals 1, y equals 1. And as t increases, does x increase or decrease? X increases as t increases. So we're going to travel along the curve from left to right. So that would be our orientation, left to right. So that one's a little easier. All right, questions on eliminating the parameter. Eliminating the parameter is really more of an algebraic exercise than anything else. The purpose of eliminating the parameter is usually to sketch the graph, to help us sketch the graph. Looking at this set of parametric equations, I wouldn't know immediately that it was this parabola. But we can eliminate the parameter and sketch this graph. All right, let's look at another kind of curve. So same thing. We want to eliminate the parameter and sketch the graph. x equals 3 cosine theta, y equals 4 sine theta. 0 less than or equal to theta, less than or equal to 2 pi. So we want to eliminate the parameter. Anybody have an idea of what we're going to do here? So here's my hint on these. Whenever you see a sine and a cosine with the x and the y, think your Pythagorean identity in trigonometry. So I'm going to say x over 3 equals cosine theta. Y over 4 equals sine theta. What's always true about sine theta and cosine theta? Sine squared theta plus cosine squared theta equals 1. So I can say x over 3 squared plus y over 4 squared equals 1. And I'll rewrite that. X squared over 9 plus y squared over 16 equals 1. What kind of graph is that? That's an ellipse. All right. So we have an ellipse. The center of the ellipse? 0, 0. Major axis, vertical or horizontal? Vertical major axis. I'm just going to say MA. And how long is the major axis? What's its length? One more time. 8. 4 is half the length. So the major axis is twice that. Length is 8. And the minor axis length is 6. So now we can sketch this graph. We have a vertical major axis, its length is 8, so we're going to be up here and down here at 0, 4 and 0, negative 4. And this will be at 3, 0, 0, negative 3. And my ellipses never turn out looking very nice, but we get the idea. So there's my ellipse. And as theta increases, what happens to x? It fluctuates, yes? When we're starting at theta equals 0, what does x equal? Cosine of 0 is 1, and as theta increases towards pi over 2, x is going to do what? Decrease from 1 to 0. So which direction are we going around the curve? Counterclockwise or clockwise? Counterclockwise. So we can say when theta is 0, x equals 3. We start here. As we trace around, as theta increases, x is going to decrease at pi over 2. X is going to be 0, and then we go negative. So we have a counterclockwise orientation. All right, so that would be the sketch of that particular set of parametric equations. We're going to get to the point where as soon as we see this, we realize it's an ellipse. We won't even need to go through this process. We'll say, oh, that's an ellipse. Its major axis is such and such, horizontal. All of that stuff that we just did, hopefully we will start to recognize that right away. All right, questions on that one? So when you see sines and cosines with your x's and y's, you should think something along these lines. That you're going to have some kind of relationship that has to do with your Pythagorean identity. All right, so eliminating the parameter, that's going to help us in sketching a graph. Often we're going to want to find a parameterization for a particular curve. We want to find a set of parametric equations that represent a curve. So we're kind of going the other way next. So we want to find parametric equations. So we'll start off with an easy example. Y equals 1 minus x squared. And usually for these kinds of problems, you will be given the parameter. They'll say parameterize it in terms of such and such. So we want to find a set of parametric equations. We're going to talk about two different parameters. So our first one, we want a set of parametric equations when x equals t. So that's my parameter, x equals t. When we have this is easy. So what's y going to be if x equals t? Y equals 1 minus t squared. And we're done. So this we just talked about the graph of this equation. So that's an easy parameterization. If you have a choice of parameters, choose the easiest parameter or choose the most convenient parameter. Let's do something a little more interesting. Let's do another. I want to do another example. That one's easy. So let's say y equals, for this particular example, x cubed plus 5. This time we want to parameterize with the slope. At a particular point. So we want to parameterize this with respect to the slope. So how are we going to find the slope? What gives us the slope of this function? The derivative. So m, our slope, is dy dx. And of this particular function, what's going to be, what's dy dx? 3x squared. So there's our parameter. M equals 3x squared. So x equals the square root of m over 3. So there's my first equation in my set of parametric equations using the slope as our parameter. And y is going to be square root of m over 3 cubed plus 5. And I can rewrite that as m over 3 to the 3 halves. So there's our set of parametric equations. So let's talk about the graph of this function really quickly. What does the graph of this function look like? It's a cubic, but it's shifted which direction? What is it, Josh? Up by 5. Our 5 is outside the function. So we have a cubic shifted up by 5. So there's my sketch of my cubic. At x equals 0, what is our slope on a cubic function? At x equals 0, what's the slope? 0. At x equals 0, the slope is 0. When x is negative, what is the slope? Negative or positive? Positive. And when x is positive, the slope is positive. So does this parameterization leave out any part of our curve? Sometimes when you parameterize your curve, you might your parameterization might leave out part of the curve. So we're okay here. So this would be my graph, and this would be my set of parametric equations. And we can choose a parameterization that's convenient for us. We chose the slope here just to give us an exercise in using something different as a parameter. Next semester we're going to be parameterizing curves a lot in terms of the arc length. That's going to be a convenient parameterization to parameterize in terms of the arc length. So questions on this example, parameterizing in terms of the slope. I wanted to go through, I don't think I'm going to do it, the parametric equation of coming up with the parametric equation of a cycloid, but I think I'll skip that. Anybody know what a cycloid is? Cycloid is if you have a circle rolling along a track. A cycloid is the path that the point on the rim of that circle takes. Looks like that. So as the circle rolls, so we can come up with a parametric equation of a cycloid. What I usually do is come up with the parametric equation. It's not particularly difficult, but it takes a little bit of time. But I have some animations that show all kinds of different curves that are generated by a circle, a point on a circle. So a cycloid is generated when you have a circle rolling on a flat piece of ground, and the cycloid is the path that the circle takes. It turns out that for a cycloid, our parametric equations are x equals a theta minus sine theta, and y equals a times 1 minus cosine theta, where theta is the angle through which the circle has a radius of the circle has turned. So let me show you these animations just because they're fun, of different types of curves that are like cycloids. Where do I have it? Here we go. So there's a cycloid. So there's our circle rolling along, and a point on that circle, and the cycloid is the curve that thing makes. And we could come up with a set of parametric equations for that cycloid. So this is a cycloid. The next one is called a curate cycloid. And this is the path that the point somewhere inside the circle takes as it rolls along. So that's a curate cycloid. The next one is called a prolate cycloid. So that would be the path when the point is beyond the track where the circle is rolling. So this would be the path like a train wheel, goes slightly below the train track. So at some point while it's rolling along, a train wheel actually goes backwards when it goes below the track. So this is called a prolate cycloid, generated from a circle rolling along. And this is a cardioid. So we have a circle rolling along the circle, and we will talk about the equation of a cardioid a little later. So just some different curves that are generated by circles rolling. All right. So Homework. All right, there you go.